the course is an introduction. This word is very important. So the idea is to cover the basics and also probably some applications as well. In particular, if you don't know anything about algebraic topology, then the idea is you will be able to take this course and hopefully learn something. How to determine whether or not you know anything about algebraic topology? Well, let's see. I will explain everything later on, but first let's look at the first question. Does anyone or everyone know what the answer is? And the answer is well, 0 or 1. It doesn't matter. Okay, so does anyone know the answer to the second question? And the answer is Z. What about the third question? Okay, what's so there are two versions. One version trivial, the other version Z, and why? Why is it trivial if it's trivial, and why is it Z if it's Z? With the Hopf vibration, exactly. Yes, so the answer is Z by the Hopf vibration. Okay, so basically this course is basically intended for people who are not sure whether or not the first group is trivial. Okay, and we'll probably talk a little bit about the Hopf vibration later on, but let me just very briefly explain what it is. The circle S1, which we, in this example, view as the group of complex numbers of modulus 1, acts on the unit sphere in C2. And the quotient is CP1, which is the same as the 2 sphere. And basically, if we take the long exact sequence of the homotopy groups, which comes with this vibration, we get this answer. Anyway, let's So this was just this was basically not a test. Well, it's a way for everyone to determine for themselves what they know or don't know about algebraic topology. Again, this course is intended for beginners, and there is no reason to get scared if you don't know the answer to the first question. And on the other hand, if you want to learn something about more advanced algebraic topology, then probably the first half of this course will be boring and so on. Okay, but so I've explained the first word, introduction. Now, what about cohomology? What is cohomology? Actually, there is homology and cohomology. Both in both cases, the homology and cohomology is a Z-graded abelian group. What does this mean? A Z-graded abelian group is the same as a sequence of abelian groups. Now, is everyone comfortable with the expression abelian group? Okay. Well,
sorry, there missed number one, isn't it?
It turns out that in the case of the ordinary homology and cohomology theory, this group will be zero,
Okay.
and h minus 2 will also be zero, and so on. But there are homology and cohomology theories for which all of those groups may happen to be non-zero. For example, K-theory, which we will not talk about in this course. Okay. Now, let's see an example. But before, I have explained the word cohomology and also homology. It's just a graded abelian group. What is a cohomology theory? I will not give the full definition. Let's just see in general what sort of object this is. By the way, if you wish to come in, please do. Okay. So a cohomology theory associates a graded abelian group to each space. Such that some properties, some conditions, axioms are satisfied. I will now list some of them, and then we'll see the rest later. Okay. Now, all the words in this sentence are presumably familiar. If not, please let me know. But just one thing: what's a space? There are cohomology theories and homology theories which work for arbitrary topological spaces, but in this course we will mainly be interested in spaces which have a sufficiently nice local structure. What does this mean? Well, this means for example, a CW complex. Now, is everyone familiar with CW complexes? No. Okay. We'll talk a little about those in the sequel. But one example of a CW complex would be a smooth manifold. Does this expression, smooth manifold, make any sense? Okay, well, every smooth manifold can be made into a CW complex, and but so can a polyhedron. Does the word polyhedron make any sense? Let's, for simplicity, let's define finite polyhedra. What are those? Well, those are just finite unions of simplices in a Euclidean space. And so on. And there is a way to define infinite polyhedra, but never mind that for the moment. Okay, let me before I explain some of the axioms, let's consider an example. But before I give an example, I will explain the notation that I will very often use. Actually, there will be these things will come in two flavors: homology and cohomology. We'll see in a minute what the difference is. But on the level of notation, in the homological case, we put the indices which correspond to this thing, Z grading. We put the indices as subscripts, and in the cohomological case, we put them as superscripts. Okay. Now, so far nothing happened. This is just a piece of notation. This is how people usually denote graded abelian groups and their components. Okay, well, now in this course we will only consider homology theories and cohomology theories such that the cohomology of a point is 0 in all non-zero degrees. We'll start with homology, and then when basically some parts of the theory extend to cohomology in a straightforward way, we'll not discuss those in detail, but there are some other parts which only work for cohomology and not homology, and we'll at this point we'll switch to cohomology. There is no colored chalk. I don't see any. Anyhow, well, this assumption is important. Moreover, today we will only consider the homology theory such that for a one-point space, the associated graded abelian group is Z in degree 0 and 0 in all other degrees. Does this make any sense? Всем ли понятно, что вообще происходит? Okay. If something doesn't make sense, please don't keep it to yourself. Let me know. Okay. Now, a few examples. If we work with the homology theory such that the point has Z in degree 0 and 0 in other degrees, then the homology of the unit n-disk in Rn will be the same. Z in degree 0 and 0 in all other degrees. In a minute we'll see some of the axioms, and we will see why we have this equality. Another example which which we will also see in more detail in a minute, is the n-sphere. The homology of the n-sphere is z in degrees 0 and n, and 0 in all other degrees. Okay, now does everyone understand what it says? Not why, but what? Okay. Okay, now the axioms, or at least some of the axioms. Well, the most important property of homology and cohomology is that both homology and cohomology are functors. A homology theory is a covariant functor from spaces well, let's say sufficiently nice spaces. CW complexes will do. Actually, this the homology theory we will mainly be talking about works for arbitrary spaces, but as I said earlier, those which will be of interest to us are spaces of geometric origin, such as polyhedra and so on, smooth manifolds, CW complexes. Okay, now the word functor, contravariant, covariant. Does the word functor make any sense? Are there people who haven't heard about functors? Anyone? If this is the case, please let me know, because there'll be quite a lot of functors later on. So it's probably best to sort this out now than run into problems later. So a homology theory is a covariant functor, which means if we have two maps of spaces, then the induced homology maps are composed in the same order, and a cohomology theory is a contravariant functor, which means the order is inversed. Well, let's before we talk about other axioms, let's consider a couple of examples. Now, before we talk about this example, let's see if it makes any sense. So the n-sphere, well, I should have asked earlier, but the n-sphere, I presume, does make sense. Okay, what is okay, let's say degree D map. A smooth map of degree D. So, does this expression make any sense whatsoever? So there are.
What means here degree of map? Is that?
Okay. Well, just let me give an explanation from differential topology. Okay, I will explain this in terms of differential topology, and then we'll see an explicit example which does not involve any differential topology whatsoever. So. Almost every point of, if we have a smooth map, almost every point is a regular value. By compactness, its pre-image is a finite number of points. Both the source sphere and the target sphere are orientable. Let's take any regular value. Let's take its pre-image and let's calculate the sign of each element of the pre-image. And the sign is +1 if locally about this point the map is orientation, preserves the orientation, and the sign is -1 otherwise. Then we take the sum. And if we take a different point, the number of elements in the pre-image is maybe different, but the sum with the signs is the same, and this is the degree.
We take non-singular point.
We take a regular point, which is and what's a regular point? Can anyone tell me what a regular point of a smooth map is?
Non-singular.
No. The non-singular points live here.
Okay.
And but once we know what a singular point is, we know what a regular point is. Or more precisely, a regular. There are singular points which are the points in the source sphere where the Jacobian matrix is degenerate, and the images of those in the target sphere are singular values, and all other points in the target sphere are regular values. Okay, so are there any people to whom this explanation makes no sense whatsoever? Well, I hope that it's some people know smooth manifolds, but understandably, some people don't know smooth manifolds. And if you don't know what a smooth manifold is, I recommend that you take the second-year course on smooth manifolds, which I think should be open to MSc students as well. The only problem is I think the course is in Russian. But there must be other courses on smooth manifolds which take place in English. Probably there is one at the independent university, maybe not. Or else you could come and see your supervisor and ask them for some advice. Anyway, knowing something about smooth manifolds is useful, but it's not a prerequisite for understanding most of what will happen in this particular course. Okay, but to be quite explicit, let's well, let's first assume that n is greater than or equal 1, or else there aren't any maps of degree greater than 2. Okay, let me give an explicit formula. I consider an element of Sn as z, comma, n minus 1 real numbers. Okay, so the first two coordinates are viewed as a single complex number, and the rest are real. And we take this to z to the power n, and then x2, xn. Does this make any sense?
The first one is it in here, which comes from C.
Yes. So this z is viewed as an element of C, and then I take
few words about why is this? I don't understand why that is Sn. When first coordinate is C, and any other are.
well. The first coordinate is something, and the second is something else, and so on. And the squares add up to 1.
That is part of Cn or not?
No. This is part of Rn plus 1. But we split Rn plus 1 as C cross Rn minus 1.
Okay, thank you.
Okay, now by the way, it's an exercise to show that this result is again an element of the n-sphere. It's not just an element of Rn plus 1, it's an element of the n-sphere. Okay, so this is an example of a map from the sphere to the sphere of, degree d. And d is an integer. Конечно.
Число мы же ориентацию можно в другой сфере. Поменять знак появился, соответственно, кажется.
Well, yes. So in this definition, we assume that in this definition we assume that in the definition of a map of degree d, we assume that the orientations in the source sphere and in the target sphere are fixed, and then we have the degree. But if the sphere is the same, it doesn't matter which we get the same answer as the degree. Basically, the reason is very simple. Suppose you have a matrix which has an n by n matrix which has a determinant greater than 0. Now, if you take the same matrix in a different basis, the determinant will be the same. Okay.
Sorry, but this map takes point, not point on a sphere. Some squares is not one thing.
Well, my claim is this map preserves the sphere.
Frankly speaking, it's really hard to get why first is sphere, but I think I get it because there are only n coordinates.
Okay.
I may explain for us.
I think it's also a good exercise to explain it in English. So could you please explain your argument in English?
My argument. I want to retell your explanation of this sphere representation, because first two coordinates is an imagined part of z complex number. Do you understand?
Yeah, I understand this.
Okay, if you make transform it to power d, you make first real part cosinus phi and sinus phi to another cosinus of sinus.
Well, actually, yes. I think you're both right in a way. Here, when I take the dth power of a complex number, the modulus changes. So which is a good remark. So we need to. If we want the modulus to remain the same, we need to insert a factor here, so that the modulus of this thing would be the same as the modulus of z. So what do? Well, we divide or multiply. Well,
Maybe by modulus of this point, modulus to the power of t minus 1 divided by this number.
Okay, well, let's see. So the map should be z goes to t z z to the d, such that the modulus of z is where t is greater than 0 is t or greater than or equal 0 okay, and then we find t as z to the d minus 1.
1 minus d?
Oh, sorry, 1 minus d, you're right. And all this works if d is no, if z is non-zero, and well, let's say t is 0 if z is 0, and then one needs to check that this map is continuous. Okay. Now, does this make any sense whatsoever?
I don't understand if we need additionally divide z by t or what?
Well, we want
in this map in the exercise.
in this map we multiply. So here we multiply by here we multiply by t, which is z to the power 1 minus d. If z is non-zero and if z is 0, we basically could take anything instead of z, any number as t, and it will work. Yes.
What we have if d is not natural?
Well, if d is not natural, then the function z to the d is not single valued. It becomes a multi-valued function, which basically does not allow one to define this map. Okay, does this make any sense? Now, my claim example. Oh, we continue this example. We know, or sort of know, that the homology is 0 in degree 0, z in degree 0 and in degree n, and what does which map of this graded abelian group does F induce? Well, my claim is in degree 0 nothing happens. we just have the identity map. But in degree n, we get multiplication by d, where d is the same d. Does any of this make any sense?
Sorry, in degree 1 nothing happens, or 0?
In degree 0. Well, in degree 1 nothing happens because, well, if n is greater than 1, then in degree 1 we have 0, so nothing happens. But also nothing happens in degree 0 where we have z. The only interesting part is degree n. So this is 0, this is n, and in degree n we have multiplication by d. Okay, so all this was to illustrate functoriality. Homology is a functor. If you were to forget everything but one thing about homology, then this thing would be homology is a functor. Never mind the rest. Okay, now let's see another example. Suppose we have a pair of sufficiently nice spaces. Let me denote the inclusion map from A to X by I. A continuous map R from X to A is a retraction if R composed with I is the identity of A. Warning, a retraction is not the same as a deformation retraction. There's a not necessarily, well, every deformation retraction is a retraction, but the converse is not true. By the way, can someone give me an example? Can someone give me an example of a retraction?
Maybe plane without 0 and circle.
Well, this is both a retraction and a deformation retraction.
Yes.
But can someone give me an example which would be one but not the other?
Excuse me, what's the equality?
Oh, here it says I.
What's an I?
Well, I is the inclusion, followed by R is the identity of A.
For example, maybe the branch of square and one of its side. You can define the projection. Квадрат одной стороны.
Well, again, it's a retraction, but it's not. Well, it depends on what the square is. Do it.
Граница квадрата.
Okay, yes, this one will do, and there is a simple way. We could take any non-empty space, such as the sphere, for example, and map it to any of its points.
Mm-hmm.
And this map is clearly a retraction.
Mm-hmm.
But very often this will not be deformation retraction. Does it make sense? Точка является ретрактом где угодно, в любом пространстве, но не всегда деформационно. Okay, so suppose we have suppose we have a retraction. Then we say that A is a retract of X. Okay, and my claim is if A is a retract of X, then for every n, we have a direct sum decomposition. The nth homology group of X is the nth homology group of A plus something. And what this something is, by the way, are there people who can tell me what this other something is?
It's the homology of factor space.
Is the nth reduced homology of X by A, and we'll see why. To begin with, let's see why we have such a direct sum decomposition. Well, we have I, the inclusion, we have R, the retraction. And the composite map, first I, then R, is the identity. And then we use the fact that functors are functors. We have a map. We have the map from Hn of A to Hn of X, induced by I. We have this. We have another map which is induced by R, and the composite is the identity. Functors always take identities to identities. Now we we have a purely algebraic problem. Suppose I have A and B, two abelian groups. And suppose I have a map from A to B and another from B to A such that the composite is the identity, then B is isomorphic to the direct sum of A and the kernel of this map. And well, it's an exercise in basically in abelian groups. Does everyone agree with what has just happened?
Don't you need exactness of the functor?
Maybe it follows because of identity.
We don't need exact sequences for this. Not
Do you need the functor to be exact to explain?
well. Every functor takes composite maps, compositions to compositions. So this part is purely formal. I have A, B, abelian groups, map from A to B, another one from B to A, and the composition is the identity. Well, then I have this. Все ли согласны с тем, что происходит? Okay. Now, so we've basically only using just functoriality, nothing else. We proved this formula. Well, let's use it. Let's use this formula to prove something. We'll prove two things. Thing number one is the n-sphere is not a retract of Sn is not a retract of dn plus 1. Well, why? Well, because and here we again assume that n is greater than or equal. Well, let's assume that n is greater than or equal 1, and then we have Hn of Sn, which is Z, Hn of dn plus 1, which is 0. And 0 is not a direct sum of Z plus anything. Does this make sense? we все ли согласны с тем, что происходит? So we have shown, using functoriality only, that the sphere is not a retract of the unit disk. So what? Well, let's and also, by the way, the same sort of argument works for n equals 0 as well.
What is sphere 0? Isn't it a point?
No. No. It's the set of all real numbers such that the square is 1. And there are two of those, plus 1, minus 1. So my claim is the same is true for when n is equal 0, but this time the argument is h naught of s naught is z plus z. H naught of d1 is z, and it is still true that z is not equal to z plus something. So the proof changes slightly, but the result remains the same when n equals 0. So we have shown that for every n, the sphere Sn is not a retract of dn n plus 1. Well, as an application of this, let us show that every continuous map from the unit n disk, again n greater than or equal 0. So we want to show that every continuous map from the unit n disk to itself has a fixed point. In other words, there is an x such that f of x is x. Does everyone understand what it says? Well, I think there probably will be quite a few people who already know where I'm getting at. But maybe not everyone, so let me repeat the argument, repeat or tell for the first time the argument. Well, the argument is this. I define R from from dn plus 1 to Sn using this picture. And this definition makes sense if f has no fixed points. What do? I take an x, I take f of x. F of x is different from x by this assumption. Then I trace a ray from f of x to x, and I look at the point where this ray intersects the sphere, and I call this point r of x. Well, if x is inside the sphere, then r of x is x, as is clear from the picture. Well, what does this mean? This means we have constructed a retraction from the disk to the sphere, and we've shown a few minutes ago that there is no such thing. So we arrive at a contradiction, which means the assumption was false. There is a fixed point for every f. Okay. Are there any questions? Okay, just one last thing. This thing is called the Brouwer's theorem. And what I've just told is more or less the standard proof of this theorem. Okay. Yes. Well, just by construction. Well, suppose we have an x somewhere inside the sphere. We have f of x, which may or may not be inside the sphere, doesn't matter. The only thing that matters is f of x not equal x. I trace the ray, and the ray intersects the sphere. The ray might intersect the sphere at its origin. So to be more precise, we consider the intersection point, which is different from the origin. And but if x was in the sphere to begin with, the intersection point different from the origin of the ray will be x itself. And does everyone agree with this? Yes.
We can write a formula for f of x.
Yes.
X is x minus f of x divided modulo.
Yes. There is a formula which involves the square root of something, and when choosing the square root, we choose the intersection point, which is different from which is different from f of x. Okay, exercise. Write a formula for r of x using square roots and and the usual operations such that plus, minus, times, and so on. And my claim is this is possible. Are there any more questions? Okay, let's have a let's have a 20 minutes break, and then we'll see some more axioms and calculate a few more examples. Так, значит, чего делать с этим? Выключать, не выключать? Well, so far we have seen functoriality, which is the first and most fundamental property of homology theory. Let's consider another property. Homotopy invariance. What does this mean? This means what it says on the board. Suppose we have two continuous maps from x to y, which are homotopic. Then the induced homology maps are the same. Okay. Well.
So we masturbate it. It is an axiom.
Say again.
Yeah, it is an axiom of homology.
If we consider homology theories with an S at the end, then this is one of the axioms. If we then take some particular construction, this becomes a property which one needs to prove. Okay, continuous probably makes sense. What about homotopic? Does the word homotopic make sense?
Yes.
Okay. If it doesn't, please let me know. Let's Well, here is an application. Suppose we have two spaces which are homotopy equivalent. Then the homology groups are isomorphic. Does this phrase homotopy equivalent make any sense? Yes. So what does this mean? This means there is a continuous map from x to y and another continuous map from y to x, such that f composed with g is homotopic to the identity of y. G composed with f is homotopic to the identity of x. And basically, straight from this definition, it follows that f and g, well, f and g induce some maps of the homology groups. And when we take the compositions, those maps become homotopic to the identities, which means the induced homology maps, when composed in this order or in this order, are the identity. Does this make sense? Okay, does this make sense?
Okay.
Well, for example, suppose we have a star-like subset of Rn. What does this mean? Well, this means what it says on the box. There exists an X node inside X, such that for all X inside X, the line segment X naught X is contained in X. Well, the picture, well, let's try to I'm not sure this picture is very good, but the idea, I hope the idea is clear. For example, we get the fact that we already used at some point the homology of the n disk is the same as the homology of a point. The disk is much bigger than a point, but the homology is the same. Okay. So we have seen functoriality and homotop invariance. What next? Well, next we need to talk a little about exact sequences. And let's see. Are there people who are already familiar with exact sequences? Well, quite a lot, actually. Okay, let's rephrase the question. Are there people who are not familiar with exact sequences? If you're not familiar, please let me know. There'll be plenty of exact sequences later on. Yes? Значит, перевод такой, что если кто-то не встречался никогда с точными последовательностями, то, пожалуйста, скажите, потому что потом этих точных последовательностей будет очень много. Поэтому, если это что-то там из области непонятного, то лучше, значит, лучше разобраться сейчас, чем потом. Ну, для начала просто определение. Значит, все ли понимают, значит, слова точная последовательность? Okay. Okay, let me erase this part. Well, to calculate or talk about exact sequences, it's not necessary, but nevertheless it simplifies things. Let's define reduced homology. Every topological space maps continuously to a single point space. We know that homology is a functor. So this map from X to the one point space has a kernel. Well, we take this we take the reduced homology to be the kernel
I'm sorry.
of this map.
Why there are unit map in это конкретное отображение?
Ну, значит, философский вопрос. Значит, давайте мы рассмотрим вопрос философский, потому что есть неоднозначность в выборе точки. Okay, let's, for the sake of this definition, let's say that PT is a topological space which lives far away from Earth, different galaxy somewhere. So it is not contained in X. So then there is so, by the way, every one-point space is a terminal object of the category of topological spaces. And what does this mean? Well, this means there is a unique map from every space to every one-point space. Now, if PT is some abstract one-point space, then we get a well-defined map, a well-defined kernel. Now, another option would be to, and sometimes it will make sense to do this. Another option would be to take PT to be some point of X, and then we get the same answer after isomorphism, but this kernel, and we shall see in a minute that this kernel is by definition this kernel is a subgroup of H lowest star of X. So depending on what PT is, the kernel may vary, but the answer up to isomorphism is the same. Значит, еще раз. Значит, точку можно выбирать там, значит, различными способами. Вот давайте мы, well, one example. Let's do one simple example. So suppose X is a two-point space. Well, let's pretend that we know that H naught of X is Z plus Z, where this Z is H naught of this X1, and this Z is H naught of the other X1. What's the kernel? And we can map X to X1, and we can map X to X2. Now the kernels will be one copy and the other copy respectively. What if we take a point in the galaxy of Andromeda, somewhere far away? Then the kernel would be the subgroup of this Z plus Z, such that the sum of the coordinates is 0. So for the sake of this definition, let's say this PT lives very far away. Okay. Are there any questions? Now we are able to state well, to oh, by the way, before I say anything about long exact sequences, I want to I want to say the following thing. Knowing h tilde is more or less equivalent to knowing h. Which basically follows from the fact that well, if x is non-empty. To prove this, we basically use the retraction principle, which we already used a couple of times before. Now, let's look at this formula. What's wrong with it, if anything?
Well, almost all homology of point is equal to 0.
Yes.
And most of the time we get the formula like h of x is equal to h of x.
Well, h without the tilde is equal h with the tilde. No, well, yes, we do get this. But there's one thing which we sort of saw in this example. This is functorial. But and so is this. Both this thing and this thing are functors of x. But the complementary summand, which is isomorphic to the homology of a point, is not functorial. Okay. For the moment, this is not very important, but it's something to keep in mind. Basically, why? Because there are lots of ways to choose a point in X, as we see in this example. Okay, but in any case. In any case, if the homology of a point vanishes in non-zero degrees, then in positive degrees, or in fact in non-zero degrees too, the homology with the tilde is the same as the homology without the tilde. Why bother with the tildes? Well, because if I have the tildes, I can write the following long exact sequence.
Excuse me, why doesn't it work for degrees bigger than 0? Why doesn't it work for negative?
Well, in degree 0, we have...
for negative degrees, why doesn't it work?
Oh, for negative, it also works, but okay, let's let's say not equal 0, not equal 0. But if the degree is negative, then we have 0 in both cases. So it doesn't really help. And by the way, there is another potential issue. Anyway, let's. There is a potential issue about how this thing behaves when x is actually empty. Let's not worry about this at the moment. Okay, exact sequences. Suppose we have a CW pair. What does this mean? Well, this means a CW complex and a subcomplex. Then we have first of all, the quotient space is also a CW complex. And we have this long exact sequence, where the first map from A to X is just the inclusion, and the second one from X to X by A is the map which collapses A. And yes?
Is that additional axiom?
Well, again, it's if we consider homology theories, it's an axiom. If we consider just one homology theory, and we want to prove that this is a homology theory and not just something, then it's a property. Now,
so is this something to be proved?
Yes, it's something that one needs to prove once one have defined those things. But for us today, it is just something we use to do calculations. Для какой пары? Давайте думать. Для вырезаемой пары. А кто знает, что такое вырезаемая пара? Так, что-то я сам не помню, значит, толком. Значит, ну, по крайней мере, это верно, если... So, in general, this, if for singular homology, this we have the same result, provided A is a neighborhood deformation retract of X, which means there's a neighborhood that deformation retracts onto X. Maybe this suffices. Maybe one needs it to be a strong deformation retract. Well, let's worry about this when we get there. So the answer is yes, this is true in more generality, but we'll look at it later in more detail. Okay, and another version of the same thing. Hn of A, this time without the tilde. Hn of X, Hn of X by A, and here I insert the tilde. Hn minus 1 of A. Okay, so there are two versions, and basically one follows from the other, and well, in practice, they both give more or less the same result, more or less, because the reduced and non-reduced homology are essentially the same for the only difference is degree 0 if we consider the homology theory with this property. I said the homology theory, but for all we know, there could be several. In fact, it turns out there is only one. Okay, so we have seen exact sequences. Well, let's use those to calculate something. Example. Well, let's calculate the homology of a wedge of two spaces. Does everyone understand what the wedge of two spaces is? Okay, so to define the wedge of two spaces, we first need to assume that both are pointed, which means we have chosen a point inside each of these. Then to
С отмеченной точкой?
yeah. Then we take the disjoint union and identify the base points. And my claim is that Hn of x wedge y is the same as h n tilde. H n tilde x plus h n tilde y. Okay, now where does this come from? Well, this comes from this exact sequence. Here again, let's assume that x and y are based CW complexes, and moreover, the base points are zero cells, and so on and so forth. Okay, we take x. We embed x in x wedge y, and then we collapse x. What do we get? We get y. And so we get this formula. Is it clear what happened? Всем ли понятно? No. So let's assume x and y are CW complexes. Well, then x wedge y is again a CW complex if the base point is a zero cell. Does this make sense? Yes. Then let's collapse x inside x wedge y. The result is y. And then we use this exact sequence. But in order to get this direct sum decomposition, we use the fact that x and y are both retracts. Again, retracts of x wedge y, and then I take this this part of the exact sequence. Since x is a retract of x wedge y, this map, in fact, is the inclusion of a direct summand. Значит, понятен ли вот этот момент? Okay, so we get this one, and then what's a complementary summand? Well, the complementary one is the kernel of this one. But the kernel of this one the kernel of this no, the complementary summand no, the complementary summand is okay. Do you want me to do this in detail?
Maybe not.
Okay.
А что в этой точной последовательности будет выступать за wedge x?
Значит, в качестве wedge будет выступать, значит, wedge мы ставим сюда, значит, x ставим сюда, y получаем здесь. Или наоборот, можем y поставить сюда, а x получим здесь.
А это x.
А почему x? почему x и x в y это CW пара тогда?
Ну, потому что, значит, мы значит, взяли два CW комплекса,
Это понятно.
склеили две ноль клетки, склеили их друг с другом. Okay, so So we have this this sequence we have this sequence which results from this one directly. Then my claim is that the boundary maps, the long maps in this diagram are in fact zero. Why are they zero? Because these maps are injective and the sequence is exact. Why are all these maps injective? Well, because there is a map going from here to here such that the composite map is the identity. So the first one is injective. So the long exact sequence splits as a union of short exact sequences, and moreover, the short exact sequences, each of those splits as well, meaning the group in the middle is isomorphic to the direct sum of the groups on the left and on the right. Does this make any sense? If it doesn't, please let me know.
I know how from set of short exact sequences we can get long exact, but by I don't know how we get another way.
Okay.
То есть у нас их много, я так понимаю, на краях склейки вот этих коротких точек у нас просто отображение в ноль.
Да, совершенно верно.
А там заведомо тоже?
Нет, вообще, вот здесь, вообще говоря, не ноль. Но в нашей ситуации, когда у нас, значит, когда у нас А это X, а X это букет, вот такой ситуации, очень специфическая ситуация. Значит, у нас везде стоят, значит, справа и слева нули. Почему? Вот это нужно понять. Вот давайте думать. Does everyone understand why I put the zeros here on the left and on the right? This is an important point. Okay. Exercise. Suppose we have a long exact sequence of abelian groups such that every map AN to BN is injective. Then for every n of the sequence A, N, B, and C, N is exact. Well, once this has been stated, it's pretty straightforward. Okay, so we get these short. We get lots of short exact sequences out of the long exact sequence. And another exercise, so this is exercise, and another exercise. Suppose we have 0, A, B, C, 0, a short exact sequence of, again, abelian groups, such that there exists, okay, let me call this map F, such that there exists a G from B to A, with GF equal the identity. Then B is isomorphic to A plus C. Okay.
Вопрос к предыдущему упражнению. Разве предыдущие два члена цепочки не фиксируют следующий?
Хороший вопрос. А что мы все думаем по поводу этого вопроса?
Ну, так как-то нет.
Значит, ну да, значит, ответ, что, значит, вообще говоря, зная какой-то кусок точной последовательности, значит, нельзя предсказать следующий кусок. Ну, например, если вот здесь стоит 0, значит, вот здесь стоит 0, то это еще не значит, что здесь будет стоять 0. Здесь может стоять что-то. То есть точная последовательность, она позволяет сказать что-то, но она не позволяет сказать всего, глядя на кусок. Say again?
Is F here, F, the taker from A to B, is it injective here or not if we have 0 from that one?
Well, what do you think? Why? Well, this map is injective because there is a map of spaces from x wedge y to x, such that the composite is the identity.
By functionality or
Functoriality.
sorry.
Yes. Does this make any sense?
Two questions concerning here. So I understand the left-hand side is an injection due to its injection, but how to say that the quotient is just reduced topology on reduced homology on Y? And second, why we can consider reduced homology here instead of just homology group?
I didn't get the first question.
Why is the quotient the homology group for Y?
Okay. Let's look at this formula. We have x by a.
Okay.
In this example, the quotient space of this by x is y. If I take x wedge y and take the quotient by x, what do I get? I get y. And the second question, why do we take reduced homology? And the answer is, I don't want to overcomplicate today's lecture by talking about relative homology. Normally, we need to put relative homology groups here, and we'll talk about those. But today, let's focus on the absolute homology groups. Are there any more questions?
Как бэдж называется по-русски? Есть у него?
Get.
Okay.
Well, in English, they sometimes also say bouquet, which is very elegant. But for some reason, I myself I say wedge. But doesn't matter. Anyhow, so we have calculated the homology of a wedge or bouquet of two spaces in terms of the homology of those individual spaces. Does everyone agree? Well, let's put this fact to use. And as an example, let's calculate let's calculate the homology of SG which is an orientable genus G surface without boundary, compact. Or in other words, it is a disjoint union of it is a connected sum of G copies of the two torus. Okay, let's look at all this. First of all, does everyone understand what T2 means?
Yes.
T2 is S1 cross S1. Okay, now does everyone understand what the hash symbol means? Okay. Well, let me briefly explain it, and the idea is as follows. We take two manifolds of the same dimension, M, N. We take out a small disk out of M, and we do the same for n. So we take a small disk out of M and a small disk out of M. We take the disjoint union.
Диск размерности той же К, да?
Yes, the dimension is the same, and then we identify the boundaries of those disks in some way. In the two-dimensional case, it doesn't matter which identification of the boundaries we take. But in the four-dimensional case, it does. So if the dimension is 2, then then it doesn't matter which homeomorphism or diffeomorphism between the boundaries we take. But in dimension 3, in dimension 4, we get CP2 hash CP2, and this is not the same as CP2 hash CP2 bar. What is CP2 bar? Is it any different from CP2? The answer is no. It's CP2 bar is exactly the same as CP2. The only thing that differs is the way in which we identify the boundaries. Обозначается CP2 с крышкой. Значит, что такое CP2 с крышкой? Отличается ли оно чем-нибудь от CP2 без крышки? Ответ, что нет, не отличается ничем. То же самое CP2. Значит, но в четырехмерии то, как мы склеиваем границы, влияет на результат. In fact, we'll see the cohomology rings of those two things are different. So in dimension 4, the result depends on the way in which we identify the boundaries. But it so happens that in dimension 2, it doesn't really matter. So, which is why we simply write T2 hash T2. Значит, в четырехмерии влияет, в двумерии не влияет, поэтому мы просто пишем вот здесь вот значит, связанную сумму и не очень беспокоимся о том, какой именно дифеоморфизм мы берем. Okay, does this make any sense? Okay. But probably you've seen this this picture at some point or another. Genus G surface in R3. Well, this is how people usually draw it. Does the picture make sense? Поверхность рода G. Наверняка встречалась много раз. Okay, so let's calculate the homology of this thing. Well, we already know the answer for G equals 0, which is something. G equals 0. In this case, as G is the two-sphere, the answer is Z, 0, Z. Well, let's take G equal 1.
Why do we say that 0 times two-dimensional torus is a two-dimensional sphere?
Sorry, say again.
Why S0 is the sphere?
Да, значит, ну, по договоренности. Well, what is the unit of the disjoint of the connected sum operation? Well, the unit is the sphere. So the connected sum of 0 copies of anything, not just T2, anything, is the sphere. But this doesn't follow from anything. It's just a sensible way to define the connected sum when there is nothing to connected sum. Well, let's have a look at G equal 2. G equal 2 is a little bit more interesting, as G is just T2. Okay, so we have the two torus. Does everyone understand what this two torus is? Well, we want to calculate the homology of the two torus. Well, let's calculate the reduced homology. Let's take this two torus as X, and let's take one of the meridians as A. Okay. So T2 is S1 cross S1. And inside S1 cross S1, we have some X naught cross S1. And this is X, and this is A. And now we use the trick we've already used a few times. A is a retract of X. Well, for an obvious reason, we just take the map from S1 to X naught. In other words, the map that collapses everything, all of S1 to X naught, and the identity map of the other X1, S1. Okay, so we get the answer. Well, sort of. Let's see if we know all the ingredients. A is a circle. So the homology of A is this. So the reduced homology of A is this. Why? Well, we saw this formula a few minutes ago. The reduced homology plus the homology of a point is the same as just homology. Well, the homology of a point is this Z, and the whole of homology is Z, Z, so the reduced homology is Z. Okay, so we know the reduced homology of S1. This is one of the ingredients, and this is true for all n. What about the other ingredient? X by A. What is X by A? X by A is the two-sphere with 2 points identified. Does this make sense? Okay, now my claim is X by A is homotype equivalent to S2 wedge S1. Why is it true? And is it true? Maybe it's false. So let me draw S2 wedge S1. Why is this space homotype equivalent to this one? Are there any ideas?
В первой картинке можно точку так растянуть,
Да, совершенно верно.
а потом стянуть
Значит, да, совершенно верно. Не обязательно строить отображение напрямую из одного в другое, значит, оно сложно. Достаточно построить, it suffices to construct, to prove that these two things are homotype equivalent. In fact, it suffices to construct a third space which is homotype equivalent to both. And the third space is S2 with a copy of the unit interval attached to S2 at 2 different points. Does this make sense? So we take a sausage and attach a string to it at 2 places. Okay, then what can we do? We can do 2 things. We can collapse the string. And what do we get? We get this space. Or we can take a path. We can take a path between the connecting points on the sphere, and we can collapse this path. And so if we collapse the path, we get this space. And if we collapse the string, we get this space. And so both maps are homotype equivalences because, well, we sort of know that collapsing contractible subcomplexes is a homotype equivalence. Okay, so we have this space S2 with a copy of the unit interval attached to it. Now let's take a path from one endpoint to the other endpoint on the sphere. If we collapse the unit interval, we get this, and if we collapse the path, we get this. Does it make sense?
The second is easier, the first is not.
Значит, что произошло? Значит, берем значит, вот эту вот сферу с отрезком, который приклеен к ней по концам. Значит, и вот такое пространство. Значит, в этом пространстве можно схлопнуть отрезок, а можно схлопнуть какой-нибудь путь на сфере, который соединяет точки, в которых приклеен отрезок. Значит, и в том и другом случае мы стягиваем, значит, что-то стягиваемое. Точнее, схлопываем в точку что-то стягиваемое. Значит, но мы знаем, что если мы схлопываем в точку что-то стягиваемое, то гомотопический тип не меняется. Ну вот, здесь мы схлопнули одно стягиваемое, получили вот это. Здесь другое стягиваемое, получили вот это. Значит, итого какой итог? Итог, что значит, и вот это гомотопически эквивалентно вот этому. Ну, а значит, они гомотопически эквивалентны друг к другу, но значит, отображение из одного в другое построить сложно, и мы даже не хотим. Okay, so as a result, we see that X with a collapse is the wedge of S1 and S2, and what's the homology? The reduced homology. Well, we take the reduced homology of S1. We already know what it is, and in a similar way we calculate the reduced homology of S2, and the result is Z in degree 1, Z in degree 2. And so the reduced homology of the two torus is Z plus Z in degree 1 and Z in degree 2. Does everyone agree? Okay. Well, this was the kj equal 1. Well, we use the same principle. We take X to be the surface of genus G. And then we want to choose an A, which preferably would be a retract. Are there any suggestions? want to use the formula, if A is a retract, we have this very simple formula, and we want to use it. Значит, нам хочется подобрать какой-нибудь ретракт вот в этом всем. Такой что? Мы знаем гомологии и его, и факторы по нему. Вот давайте подумаем.
Ну, собственно, мы проходим, мы берем точку, проходим окружность по одной дыре, по другой. Если это как-то полностью.
Значит, нам нужен ретракт. Это подмножество.
Так, хорошо.
Вот какое подмножество?
Каждую ручку охватывает.
Ну хорошо, а почему это ретракт? И будет ли оно ретрактом?
Ну, как будто нет. Нельзя.
Сейчас, но если считать, что у нас окружности как бы вдоль каждого отдельного тора они касаются там, где торы склеены, то казалось бы это как раз ретракт, потому что можно на это смотреть как на сейчас. Да.
Ну, значит, тор ретрагируется на окружность, это да. Но у нас сейчас не тор, у нас что-то такое более сложное. Если там каждый тор ретрагирует на свою окружность, то не очень понятно, что происходит посередине.
Ну, как раз нужно, чтобы они касались посередине, чтобы это были окружности, которые как бы... То есть вот здесь вот это была бы такая вот длинная цепочка из окружностей. Они касаются посередине, и вот ту окружность, по которой торы склеены, в точку касания.
Так, значит, мы каждый тор хотим ретрагировать на что? На вот какую-то такую штуку, да?
Кажется, на сферу уже, вот этим еще же окружность. Тогда все получится.
Так, значит, вот на такую штуку не ретрагируется.
Почему? Нет,
Значит, почему?
Не похоже, что это реагируется просто.
Почему? Ну вот, значит, доказать, что это не ретрагируется, мы сможем, когда поймем умножение. Значит, пока у нас просто абелевые группы, значит, у них никакого умножения нет. Потом будет кольца, и вот тогда-то мы развернемся. Но пока не можем.
Может быть, одномерный скелет?
Что еще раз?
Одномерный скелет, как целый вопрос.
Значит, одномерный скелет. Одномерный скелет тоже не ретрагируется. Но вот опять же, значит, потому что есть умножение из H1 в H2.
Стоп, дизъюнктное объединение окружности.
То же самое. Ну, дизъюнктное объединение окружности это еще более невозможно, потому что значит, вот эта штука связана, а дизъюнктное объединение не связано. Let's switch to English.
If we have just one circle, and if we retract one side to it and another side to it.
One circle. Let's. Let's think. Maybe it works. I need to think about one circle, but let me. We're running out of time, so let me give one possible strategy. There may be others. So let's take A. To be the last handle. Now, A, in this case, is the two torus minus a disk. And this is homotopy equivalent to S1 wedge S1. Whereas X by A is the same as G minus 1. And what is not entirely straightforward, but sort of straightforward after you think a little, A is a retract. Of X. Why? Well, basically, look at the next handle. On the next handle, we can just take the reflection in this hyperplane. So take this handle, reflect it, and then we map all the remaining part onto basically we can reflect it, then change the map by a homotopy so that the boundary circle goes to a single point, and then we map all the rest to the same single point. Does this explanation explain anything at all?
May you please say again what happens with the disk?
Okay, first take the reflection.
Okay.
Then we change the map on this handle. Then we change the map a little bit by a homotopy, so that this next circle goes to a single point.
Okay. That point's
somewhere here.
Okay.
And then we map all the rest of the surface to the same single point. Значит, еще раз то же самое. Значит, вот берем следующую ручку. Значит, сначала просто отражаем относительно вот этой вот гиперплоскости. Да? Значит, потом шевелим отображение гомотопии так, что вот эта вот окружность переходит целиком в точку. И потом в эту же точку отображаем всю оставшуюся часть поверхности. So, this A is a retract, and we basically use the same formula. And let me just write the answer. And the answer is Z to 2G in degree 1 and just Z in degree 2. This is, G. And if we want homology, not reduced homology, but just homology, unreduced homology, we just add an extra Z in degree 0. And this is it. Okay. Now we've run out of time, so we need to stop. Are there any questions? Say again? Reference. Well, this course does not follow any particular book, but there are several good books on algebraic topology. In particular, I would recommend Hatch's book, and we will not be able to cover everything there is in Hatch's book, but we will cover more or less the same material. And also there is a book by Fuchs and Fomenko, which is available in both in English and Russian. До свидания. Okay.